Hello and welcome back. I'm Matthew Lay, and in this lesson we are going to continue our series on combination circuits. In this particular lesson we're going to study series parallel circuits. So let's get started. We do have some objectives for this lesson. We are going to name, or in this case rename, the two types of circuits that can be made using three resistors that aren't purely series circuits or parallel circuits. And we are going to then define a series parallel combination circuit, and we're going to go through the steps to solve that series parallel combination circuit. They're a little bit different than they were for the parallel series combination circuit. Okay, so this is a little bit of a review. We've given three resistors. How many different configurations can we make? We can make a purely series circuit by putting three resistors in series. We can make a purely parallel circuit by putting all three resistors in parallel. And that is well understood now by this point. And we did in the previous lesson study the parallel series circuit. Just to review, the parallel series has no component that has total current flowing through it. The major circuit is a parallel circuit, and then at least one of the branches, and it could be multiple or all of the branches, have series circuit components within them. The last one is this series parallel circuit. And this one differs from the previous circuit in that this component right here is going to have total current flowing through it. Since current is common in a series circuit, that's why it's the major circuit on our combination circuit here. That's why it gets its name series parallel. And the parallel is a subset of the series circuit where we're actually going to divide off that total current into two different branches in this case, and then they're going to combine back together here to go back to the power source. So let's dive into this series parallel circuit a little bit further. First, let's give a definition. It's a circuit whose major current path is a series circuit. Okay, and that's defined by this component right here has total current flowing through it. And the minor circuit contains components that are connected in parallel. And the major characteristic of a series parallel circuit is at least one component of the circuit has total current flowing through it. We couldn't say that for the parallel series, but we can for the series parallel. Okay. To obtain to solve, we're going to obtain first the total parallel resistance of this minor circuit here, and then we're going to work our way out to the series circuit from there. And we're going to, in the remainder of this lesson, go through a problem. Okay, so here's our example problem. If the givens look familiar, they're the same ones that we had on the previous example for parallel series. So the only thing that's changed here is the configuration of the three resistors. So we want to solve for the total resistance in this minor circuit, and total is really in quotation marks. It's the total resistance of the minor parallel circuit. It's not the total resistance of the circuit. Okay, so here's where we use these node letters again, this A and this B. RAB is going to denote that resistance, the total resistance of that parallel circuit. And we're going to use the conductance method to do so. So we're going to invert the R2 and R3, or in other words, find the conductance of R2 into R3. And in a parallel circuit, conductance is additive. So we add those two together, and then we can get the total conductance. Of course, we're really after total resistance, and we know that the total resistance is the inversion of total conductance. So that's why I'm showing the sum of the two conductance formulas, and then we're inverting that. We're going to wind up with 333.333 ohms. Now, this, because we're just talking about this parallel circuit, this the mental check that we do, that this should be lower than any of the individual resistors in that parallel component, and it is. So that has a rough check of working out for us. We can now, I'm showing over here kind of a theoretical resistor in place of that parallel circuit. And that theoretical resistor would be of the value RAB. And now if you notice, if I do that, what do I have? I have a series circuit of two resistors. So I have simplified down my circuit, and now I'm going to move forward with all the characteristics of a series circuit to solve the sum of the quantities moving forward. So first we want to obtain total resistance of this major series circuit, and in a series circuit, resistance is additive. So we're just going to add R1 to that RAB, and we're going to get our total resistance. So if we take 880 ohms of R1 and we add in the RAB that we just calculated up here, we're going to get the 1.213 K ohms. Okay, so that's our total resistance of the major series circuit. That is the resistance that this power supply is going to experience. Okay, and so here we're just going to fill it into the table for total resistance. If you notice, there is no spot in the table for RAB. That's kind of a subset of a calculation that we do for finding these other quantities in the table. Okay, so now we're going to move forward. We're going to calculate the total current using that total resistance. And so the total current this is just using the ohms triangle, and it's the voltage divided by the resistance. So our given voltage is 25 volts, and that total resistance that we just calculated is 1.213 K ohms. And that is going to equal a total current of 20.604 milliamps. Now we want to calculate the voltage drop across R1, because we know the total current going through it and we know the value of R1. So again, we're just going to use Ohm's triangle, and E equals I times R. And so here, 20.604 milliamps times my 880 ohms is going to be 18.132 volts. That's what we're going to find across here. So we know in a series circuit that voltage is additive. So we know if we have 25 volts here and we have 18.132 volts here, the remainder of the voltage would have to be across our little parallel circuit here. So we're going to go ahead and compute the voltage across that circuit just by subtracting the 18.312 from our 25, and we get 6.868 volts. And that's going to be the voltage across this little circuit here. Of course, now we can use that to find our branch currents through those resistors. But first we're going to put our currents and our voltage drops in our table there. Okay. Now, again, remember, in these combination circuits, I can't add all of these numbers together and get 25 because these two are the same voltage. So I can add these two together and they will equal 25, but you can't add all of those together. Okay, now that we know our individual voltage drops, we can calculate our parallel branch currents. So what we're going to do is pretend like we just have a parallel circuit, and our EAB that we calculated earlier, we're going to pretend like that's a theoretical power supply that we have across our parallel circuit. And if we do that, it's just like we were solving parallel circuits like in the previous study. So EAB is going to be 6.868 volts, and we just use that as our power source for that parallel circuit. So EAB divided by the R2 will give us the current through that particular resistor, and that's going to be 6.868 milliamps. And then EAB of 6.868 volts divided by my 500 ohms of R3 will give me 13.736 milliamps, which is double the current that flows through the higher resistance, because the R3 is half the resistance of R2, okay? So, and if we add those two together, we're going to get back to our total current that we had previously calculated. So these two right here will add up to this value here. Again, you cannot add all three of those numbers to get to this current here. This is total current. This is the divided current in our sub-parallel circuit. Remember, a parallel circuit is a current divider. And so you can add those two up and get that value or that value there, okay? Now all we have to do is solve for our powers, okay? So to solve for our powers, we're just going to use our Ohms wheel. For the first one, since current is common, I'm going to use the current squared times my resistance value. So the current that we calculated was 20.604 milliamps squared times the 880 ohms that was given for R1, and we get 373.582 milliwatts of power dissipated in R1. Remember that power only is expressed in heat through a resistor. Of course, if it was a light bulb, it would be heat and light. But in this case, it's only heat. Okay, so our P2 would be calculated a number of different ways. But here, since we know that we have a voltage drop across that branch circuit of 6.868 volts, I'm going to use that and the resistance together. If you look up the formula on Ohm's wheel, it's E squared divided by R. So 6.868 volts squared divided by the 1 k ohm is going to be 44.703 milliwatts. So that will be the power dissipated by R2. And then I'm going to use that same formula for R3 and get 94.389 milliwatts for R3. Now, one of the things that is consistent across series circuits, parallel circuits, and both types of combination circuits is that power is additive. So if you take your individual power draws for, in this case, the three resistors, and add them up, that will be the power that has to be output by the power supply. And if we sum all those together, we get 512.674 milliwatts. Okay, going to go ahead and do my little check here, and this is where, each one of these is rounded off to 3 decimal places. And when we do that, especially when we're using squares of some of the numbers, we are going to get a little bit of a different result here. This is just using the current times our voltage, total current times total voltage. And I do get a little bit of a different number there. And I just wanted to show the students that that is a possibility. You could have done everything right. The only way to get it perfect is to actually be storing the actual resultant of each one of these in your calculator and then using the non-rounded values to calculate your totals, and you should get exactly matching totals. But this is a close enough check for to know that we have everything calculated appropriately. And we go ahead and round out our table, filling in the rest of the values there for our power. Okay, let's review the 2 types of circuits that can be made using 3 resistors. This is a double review because we talked about this already in the previous circuit. But parallel series and series parallel, of course, we could also make a purely series circuit or a purely parallel circuit. But these are the 2 different types of simple combination circuits that you can make. Let's give a good definition for a series parallel combination circuit. If you want to pause the video, you can, and then come back. Okay, so a series parallel circuit is one. The major path is a series circuit. And we know that because we would have total current going through one of those components. And the rest of the circuit, or at least parts of the circuit, are parallel in fashion. And we could have a series parallel. It could be a lot more complicated than what we had in this example. but the steps to solving it are still the same, okay? And just restating, at least one component in that circuit has to have total current flowing through it for it to be a series parallel. If that statement is false, then it is a parallel series combination circuit. Okay, so let's go through the steps of how to solve this series parallel combination circuit. First, we want to solve that interparallel resistance, and then we want to calculate the total current through the circuit, and then we can get our individual voltage drops. And from the voltage drops, we can get branch currents in the parallel branch, and then using our ohms triangle and the watts triangle, we can calculate our power dissipation of each one of those components. The one thing that is consistent among all of these circuits is power is additive. So this concludes our lesson on series parallel circuits. I hope that was helpful, and we'll see you in the next lesson.